So this is joint work with Vinicius Albani, who was a former PhD student of mine, Mateus Gracelli, and a number of other people. I'll discuss this group later. Basically, my talk is going to be discussing issues on epidemiology, and in particular, the relation between the pandemics that affected us tremendously in 2020, not 1920, 2020. I'm not so old. And I'm going to discuss some questions and the proposed approach, go through a little bit of the relation to the economics and the social issues, and some conclusions. But before that, I need to tell you a little bit of a story. The story goes back to 2019, when I came here. I was a professor at IMPA, Brazil. I don't know how many of you know about IMPA. Happens to be, Brazil is a small country in South America now. And I did most of my career there after my PhD in Berkeley and working in California for a while. So I happened to arrive in 2019. I was fascinated by Abu Dhabi, as many of our colleagues here are. And everything was well, good, happy. I was working in a university with about 4,000 students, 400 faculty, 10-to-1 student ratio. Great environment, 2 campuses. We have 3 colleges there. One is the newly established, now I'm jumping to 2023 or 24 perhaps, College of Computing and Mathematical Sciences. But all of a sudden, Christmas comes, I come back, I spend New Year's here, good place to be for New Year, by the way, and start some strange cases popping up. All of a sudden, you see the news. Oh, there's a kind of thing going around in China. Well, that was the beginning of the pandemics. So with the pandemics, I was locked down. Fortunately, it was not so bad here. Actually, it was a very mild lockdown. I assembled a team. Some of people were listed here. In particular, I had collaboration of a former student of mine, Vinicius Albani, and Eduardo Massad, who is a Brazilian epidemiologist, very well known. So if you go back to the history, you see this beautiful graph, March 1st, 2020, and countries started to picking up, and the rest is history. I'm sure many of the people who are here were actually participating in this saga as not only subjects, but also as data analysts and thinkers. In particular, we had Marcos Lopes de Prado and Alex Lipton. I'm going to mention the paper and their insights later. So anyway, the story goes on, and you see these peaks. You see, in fact, peaks coming back and forth. And so we started asking the question, how can we model it? Well, I come from a background of basically data analysis, data science, but with a different name that many people perhaps don't know, called inverse problems. I'm going to repeat, inverse problems. Inverse problem. Direct problem, inverse problem. So we look at it from basically a different perspective. By the way, it goes back to names like Tikhonov and in Russia, and names like school in England, school in Italy. So anyway, my idea was, can we try to use what we know about data analysis, which we have been, by the way, using in financial data, in this problem? So our approach is data-driven, and I'm going to say that it's data-driven. However, it's not data-driven in the usual way that you just try to fit whatever you can with whatever tools you have, such as, for example, neural networks and things like that. We actually build in a model, usually a model that depends on infinitely many parameters, but of course that's not feasible in practice. So we take the perspective that we are approximating degrees of freedom in an infinite dimensional space. I don't want to scare you, just don't get scared, it's okay, I'm not going to bite with those words, but it's a very big space. And we try to use as much data as possible. Now, if you have more parameters than data, of course you're going to do a fitting. Anyone here who has looked at this is going to say that. How do you approach then? Very simple. You have to put a priori information. You have to put consistent conditions. That's where, for example, the name Tikhonov regularization comes into play. And so this was our approach. Let's try to use what we know from inverse problems to approach this. Of course, by that time, we're all familiar with the statistical literature. We're following the statistical literature. So we are actually using the convergence of statistical inverse problems. Okay? Now, just to give you a glimpse of what we're heading to, we're not just trying to fit or make simulations, we're trying to see the impact of our simulations or our results in the economy. And with Gracelli, we actually jumped or plunged into a project on connecting unemployment with data analysis from COVID. Okay? And of course, the impact on the GDP. So, by the way, the graphs that I just showed refer to the critical moment, 2020. And before that, so you see this tremendous jump on unemployment and the GDP forecasts throughout time. So this 02 2020 that you see there, sorry, 02 no, quarter two, I cannot even read anymore. I don't speak, I don't hear, now I don't read. So anyway, that's okay. Can get worse. Now, to drive the point that this is a very, very important issue still today. By chance, I was reading the New York Times while, preparing this talk, and I opened October 31st. Please, also, I was supposed to send this before that, but it's okay, I did it after. And this is an article from October 31st. What is coming up at New York Times? New COVID variants, something called HV1, EG5, and there's a very interesting article signed by this journalist Donna Smith, and it's very, very actual. It's very present problem. So, what are the relevant questions? First of all, we ask the question how to simulate, how to monitor the epidemic's evolution, how to connect such evolution with financial and social data, how to take into account the spatial component, how to monitor effectiveness of vaccination and social distance programs, and how to tackle underreporting and vaccine effectiveness. Now, as I said, our approach is a mathematical approach. Needless to say, I wouldn't be in the math department if I was not doing that. Data-driven from inverse problems and statistics. We do sensitivity analysis, and we do in-sample and out-sample analysis, of course. This talk is going to be based on a number of works. I'm listing some of these works with my collaborators, published in BMC, Vaccine, Scientific Reports, Journal of Risk and Measurement. In fact, that paper, what I'm talking about mostly in this talk, is published in the Journal of Risk and Financial Management and Royal Society. I'd like to acknowledge, unfortunately, I got to read those papers much later. I wish I had known Marcus and Alex back then, because otherwise we have collaborated much more. I acknowledge a very interesting paper by Alex and Marcus on the mitigation strategies for COVID. It's a beautiful paper to read. I also like to acknowledge some papers that I learned post facto from colleagues here in the Abu Dhabi area, in particular my friend Elena Beretta and Alberto Gandolfi. So those are relevant literature that should be cited. So now, what are the highlights of our research? What kind of problems do we actually attack? We use a susceptible, exposed, infected, recovered type model to simulate and monitor the epidemic's evolution for spatial temporal data. Now, I love the K that Marcus and Alex used before the SEIR. The K refers to K compartments within each of those different compartments. And in a certain sense, we didn't use the K, but we highlight that in the spatial aspect of the problem. The implementation is done mostly with data from the COVID-19 pandemics, but it is actually, in a certain sense, a tour de force of how to use available data to track epidemics. And we definitely believe that this could be used in different contexts. Our model works a lot, or most of the time, we consider age group, gender, location. The mixing is accomplished by means of time-dependent infection rate matrices. That's why I say we have a lot of matrices, a lot of parameters, and that makes the problem a big data problem in many aspects, both from the part that you have to adjust for a huge number of parameters, and you have to somehow put together a model that makes sense. Now, the model, in the first examples we did, was calibrated from New York City data and its boroughs. That's the spatial component. We broke New York City in different boroughs. Bronx, Manhattan, you name it. So we include census data, proportions of infections, death rates for different ranges. This was available. I'll show you the site where we got the data. And we obtain a model that matches the reported curves and actually predicts fairly accurately infection information. So that's the outsample part for different locations and age classes. It allows scenario generation, simulations, and optimization of different mitigation strategies. Now, back just a little bit of history. Kermack, McHendrick, this approach for disease dynamics have been proposed since at least back then. SIR and SEIR models are the most well-known class of models. However, the problem with those models is that usually they lump everything together, and that's why it's so important to compartmentalize, to work with vectors. There's classical references there for those of you who want to follow up from the background. Now, the COVID pandemic drove attention to the scientific community, as I said, and there are many entry-level fitted data trying to fit parameters that led to catastrophic predictions. And after some time, of course, this proved to be totally unrealistic. So we tried to also put into the model adherence to social isolation and lockdowns. So are SEIR models useful? Well, if you do it all lumped together, you don't expect much adherence to the data, but there are lots of improvements. One thing that we really took care of was the quarantine and mobility restrictions. And of course, the big issue here is the bottleneck from big data. This is a place where certainly high-performance computing could be used. As I said, we do model calibration, but we avoid overfitting. We really work carefully on that. There's a lot of theory on this from the inverse problems community. Perhaps in a few years it's going to be use another name, but anyway. So the model assumptions, we are basically in the context of KSEIR using Marcos and Alex's terminology. Time-dependent parameters accounting for age, so not for age, for age and range and gender. Accounting for spatial distribution. Now, for each age range, the interaction between susceptible individuals and those infective, they are actually classified according to mild, severe, and critical. Critical are the ones that are at ICUs. The interaction from the different age ranges is inside a given location. We are not going to assume for simplicity, but it could just would make the problem much, much worse, that the different age ranges interact in the same region. Like Manhattan people don't hang out very much with at the same age with people outside, but they move from another area, and the same age interacts with the same age in, let's say, Bronx. Okay, this is just to cut out the number of parameters a little bit. As I said, it could be avoided. There's interaction between different places, and all those interactions are described by the different parameters. So this is the structure of the model. I'm using a weird notation here. The two dots, they refer, the semicolon refers to matrix multiplications, and so you have a vector and a matrix, and it's actually tensorial multiplication. So just to give you a typical glimpse of the equations, these are the equations. I'll let you look at that. Okay, you can now go back to your mobiles and send messages. But the susceptible, exposed, mildly infective, hospitalized, ICU people, recovered, deceased, all of them have rates of changes which are modeled and carefully analyzed. And everything here, S, E, I, and so on, is a vector, okay? So this is the distributed part. As I said, transmission parameters, beta, the infamous beta that New York Times likes to talk a lot, but this is a matrix just to harass people. So hospitalization rates, and so we have the daily percentage of hospitalized people, the death rate in hospitals, and we have, with those rates, we can do a lot of, how do you call, predictions, modeling. We did something for Chicago. Data, as I said, comes from this site. I'm sure that anyone who has worked on this knows about this site, the New York City government site, and you can get the latest data. I still believe this site is alive. Now, I showed you some moving window there. Is usually we break the set of daily reports into subsets of 20 consecutive dates. We break the set of unknowns into time-dependent and time-independent. There are things that are really time-independent, and there are things that are really time-dependent. Depends on the interaction, depends on social distance, depends on vaccination. And we calibrate time-independent unknowns for each of those 20 days. We calibrate the time-dependent parameters for daily data inside the sets of 20 days. Turn-off regularization, this is what people know usually in data science as something akin to ridge regression, different variations. Actually, Tikhonov regularization is much broader than that. And we do bootstrap to generate confidence intervals. So this is in-sample modeling. So you see there the reported and the estimated, and we have the confidence intervals drawn there. Okay. That is for mortality, yeah. Actually, sorry, I take that back. I think that's individuals infected. I can check in the paper, okay? But, okay, 5 minutes, oh wow. This is for Staten Island, Brooklyn, Queens. Now, new infections, yeah, now this is infections. And of course, we stop and now we do out of sample. And you see that with out of sample, you can compare the true rates with the actual rates. We have new hospitalizations, the new deaths. So the mortality, Alex, you're right. Good eye, thank you. Better than the speaker. Daily new deaths, daily new infections. So daily new hospitalizations. For Chicago, we also get similar, and I believe I take them as good results. Now, what happens if vaccination comes across? And the question that we are addressing in a paper with my collaborators is the following. Suppose you delay vaccination for, let's say, 1 month or 2 months. It's a public policy question. How many more people would get infected? How many more people die? And so we did this in October 1st, and we projected. For Chicago, it has this, let's say, not so bad behavior, but New York City would have been catastrophic if you delayed vaccination. And this is what our model was saying. This was a big debate back in Brazil, because in Brazil there was lots of time that took to people getting vaccinated. So another issue that popped up was underreporting. Many people here in Abu Dhabi, we had to report no matter what. However, in many places, you could not report. Now, the question is, how often do people underreport? It turns out that by looking, and we found a way of looking at the data and estimate the underreporting. Now, how do you check if our estimates are correct? In some countries, they do seroprevalence. In Denmark, for example, they had very good tests, and they predicted about 3%, 2.77 from the seroprevalence. From our studies, we predicted 3% not using the seroprevalence. So it's a way of double checking what we are getting from the predictions. Just very briefly, labor market. If people get unemployed, they stay home. They don't transmit, so there is an interconnection, yet you want to know how these things go. So we broke the groups into employed and unemployed. That's a superscript that you see there. And we have the blue part with the data, with the part that's not blue is the out of sample projection. The projection. And the question is, suppose now you do vaccination. And you do vaccination every 270, 360, 390. Well, then you can make a prediction of what's going to happen. Now, the unemployed dynamics, we followed kind of more or less accepted model. And we estimated for the different provinces in Canada, and we did in-sample simulations, out-of-sample predictions, and long-term predictions of infections, long-term predictions of deaths with the different scenarios of vaccinations, And we also connected with the GDP. So we had to estimate the GDP from this Okrum method. And we, in this case, had in-sample and long-term predictions of unemployment. Long-term predictions of GDP according to the different booster doses. So I close by saying we developed an epidemiological economic model. The model performs well. Short-term out-of-sample predictions have a calibration error below 5% and prediction error of 20%, below 20%, which is comparable to other models. Long-term prediction exhibits endemic cycles, and further work would be to do cross-country comparisons. So thank you very much for your attention.